All right, today's topic is U-substitution, or more specifically, integration by U-substitution. This is a technique that it greatly expands the number of integrals that you're able to take. So let's just start by reviewing the integrals you can take so far. So far you can do two basic things: the power rule, where you can have x to any power and you add 1 and then put that on the bottom. For example, x to the 4th over 4. And we had some funny powers like negative 5/4, but the rule still stays the same. The power rule works that way. Increase the exponent by 1 and then put that same value on the bottom. And we also had 6 trig antiderivatives that you can take. And those are just the opposites of the 6 trig derivatives that you learned how to take before. So as of right now, you can do these two main categories, power and trig. And before we get into the U-substitution, I want to review the chain rule. The chain rule is what let us greatly expand the number of derivatives that we could take. And that's what substitution is going to do for us for integration. But the chain rule basically said, we have some rules for derivatives. The derivative of sine of u, and if you look at the front cover of your book, u corresponds to this u. All of the formulas are written in terms of u. The formula in the book says derivative of sine u equals cosine u times u prime, or times du. And the chain rule was where we learned that if you were taking the sine of something more complex than just x, meaning it had a derivative other than 1, you had to tack on this extra u prime. That was the chain rule. So the derivative of sine of x squared was cosine of x squared, just like the rule implies. However, because the derivative of x squared is 2x, we had to multiply our answer by 2x. This is called the chain rule. Sine squared x, these two are often confused, but sine squared x, this is a power rule. The derivative of u to the nth power equals n times u to the n minus 1. This is where we drop, times u prime. I don't want to forget the chain rule. This is where you drop the exponent down, you decrease it by 1, and then you use the chain rule. So this is actually a power rule, 2 sine to the first x, and the derivative of sine is cosine. So those two are examples of the chain rule, where we were allowed to use our derivative rules on things that were a little bit more complex than just x's. So x squared in the top one and sine in the bottom one. Now let's put these ideas together. All right, U-substitution. Basically, it's the opposite of the chain rule. We can do, as of right now, the antiderivative of cosine. And up here at the top, the antiderivative of cosine of u du equals, remember your 6 rules, antiderivative of cosine is positive sine plus c. Now, up until this point, this u has always been x, and this du has always been the number 1. So we didn't have to worry about what else was inside this integral, because it was kind of like our derivative rules. We started out just talking about x's. Now we're talking about functions that are more complex than just an x. So we need the du to be there before we can integrate this function. We need this 2 dx to be there because that's the derivative of u. So let's let me show you how this is going to work. We're going to apply the cosine rule that I just showed you. However, it's not cosine of x. We're going to do this little substitution. If the thing I'm taking the cosine of, we call that u because it's a function, it's not just an x, then its derivative is 2. Technically, it's 2 dx. That's a kind of a symbolic dx. And we can talk more about why you have to put that dx, but basically, that 2 dx is all the derivative of 2. Now, if I literally substitute, I get the cosine of u du, because I'm replacing 2x with u, and I'm replacing 2 dx with du. Now it looks exactly like the formula in the front of my book. My answer is the sine of u plus c. And I don't want to leave my answer in terms of u. I want to substitute back what u equals, which is 2x. Sine of 2x plus c is my answer. Now, how is this the opposite of the chain rule? Well, if you wanted to take the derivative of sine 2x, you would get cosine 2x, but then you would tack on that extra times 2. When you do the chain rule, that other derivative just shows up out of nowhere, and you just have to add it in there or multiply by it. It just pops up out of nowhere. Well, when you do U-substitution, you're doing the opposite of that, and this 2 that needed to be there before we could start, it just kind of vanishes, and it's not part of my answer. The antiderivative of cosine 2x is sine 2x, but only if this is there serving its purpose, and then it disappears just like in the chain rule when it appeared out of nowhere. So let's try this next one. 1 plus 3x cubed times 3dx. If there's a set of parentheses raised to a power, a lot of the time that's going to be your u. The trick here is deciding on u, and you might have to try a couple options when the problems get a little more complicated, but if you can decide what u is, then you're in good shape. The derivative, du, is just 3. Again, it's 3dx, and we'll talk about that dx, but for now, just know it's 3dx. So if I substitute, I have u to the third du. And my power rule for integration, u to the nth du, is equal to u to the n plus 1 over n plus 1 plus c. So the antiderivative of u cubed would be u to the 4th over 4 plus c. And now substitute back 1 plus 3x to the 4th over 4 plus c. So this is the opposite of the chain rule, because this little 3 that would show up if I were working this in the opposite way, that would be the chain rule applying, it needs to be there to start, and then it just kind of disappears out of nowhere. Okay, the key to this slide is this du that's in the formula every time. It's something that has to be there before you can apply these rules. So let's see what happens if it is not there. Okay, what if you do not have du? So again, the antiderivative of u to the nth times du, or times u prime if you prefer, either way, same thing, is u to the n plus 1 over n plus 1. But this du is part of the formula. What if it's not there? So let's do this next example. When you see parentheses raised to a power, there's a very good chance that that's going to be your u. That's the substitution I want to make. I want to take out the contents of the parentheses and put in a u. So the formula I'm trying to apply is u to the 4th times du. Well, du equals 3x squared. Now, I don't have a 3x squared dx inside my integration symbol. I have an x squared and I have a dx, but I do not have a 3. Now, the answer to this question, what if you don't have du? As long as you're only lacking a constant, then that's no big deal. We can fix this problem. If you are lacking a constant, meaning if you have an x squared and you need there to be a 3x squared, just multiply your x squared by 3. Just squeeze a 3 in with it, and now you do have 3x squared. Now you can't just do that without any consequences. You have to compensate for that with a 1/3 on the outside of the integral. 1/3 times 3, and constants can move across the integration symbol freely, so I haven't changed my value because 1/3 times 3 is 1. But I did fix the problem of not seeing du. Well, that 1/3 that I add needs to stay there, and on the inside, I have u to the 4th du, just like I wanted. These parts, 3x squared dx, that makes up du, and then the rest, u to the 4th. So the antiderivative of u to the 4th is u to the 5th over 5. I can simplify, make it u to the 5th over 15. But eventually I need to get the u's out and the x's back in. So I'm going to make it x cubed plus 5 to the 5th over 15 plus c. Okay, this U-substitution is a temporary thing that lets me get the integral taken, but don't forget to go back to your x terminology at the end to get your final answer. Okay, next we're going to integrate cosecant squared of 2x. If you either remember or look up, Your formula for the integral of cosecant squared u du is, remember that, it's the opposite of our derivatives. It's negative cotangent of u plus c. So I can apply this rule to this particular integral as long as I have du present. So u is going to be 2x, du is going to be 2 dx. The derivative of 2x is 2. Now I see dx, but I am lacking a 2. I need there to be a 2 in here with dx. Now I can't just do that with no consequences. I need a 1/2 on the outside, and now I'm ready to go. 1/2, if you multiply by 1/2, then that 1/2 stays with you throughout your answer. The antiderivative of cosecant u du is negative, which I can put to the outside of the 1/2, cotangent of u plus c, or cotangent 2x plus c. So remember, as the chain rule just made things like 2's appear out of nowhere, the U-substitution makes them vanish into nowhere, not part of our answer. All right, here's a couple. I'll encourage you to pause this and try these and see how you do. Choosing the U is the trick, but I'll give you a second to pause and resume. So I've added our power rule up here in yellow. And remember, I can do other things to the 4th power now, not just x to the 4th power. And there's no reason those, quote, other things can't be trig functions. If you let u be tangent of x, hoping to do u to the 4th, then the derivative of u, the derivative of tangent, is secant squared. So I have exactly what I need. Secant squared x dx serves as my du, and my integral is the integral of u to the 4th times du. Okay, if your u is a trig function, this is a power rule that we're using. It's just that the base of that power happens to be a trig function. No problem. The antiderivative is u to the 5th over 5, and u was tangent. So my answer is tangent to the 5th x over 5 plus c. All right, one more, and I'm noticing I need to change. I'm flip-flopped. This needs to be x cubed inside the parentheses. So anytime you see an expression in parentheses raised to a power, that is almost always going to be u. Now this is on the bottom, so it's actually to the negative third, but that's okay. I can do power rule with a negative power. I still just add 1 as I would normally. I just need there to be a du present inside the integral. So du would be 3x squared dx. Now I am close to having 3x squared, but I'm lacking the constant, which is the 3. So I need there to be a 3 along with this dx. So 3x squared dx is all going to be du. That is here. That's the part that's going to disappear, just like it appeared for the chain rule. But I can't put that 3 in there without multiplying by a third on the outside. So my answer is going to be a third of, or actually my integral before I take it is going to be a third of the integral of u to the negative 3 du. This bottom part is u to the negative 3 after I sub out the inside and put u in its place. The du is all in the red circle, so this is everything that's left after I substitute. Now the antiderivative of something of u to the negative third is u to the negative 2 over negative 2. Remember that's attempting to make that a 4 or a negative 4 when you're adding 1 to negative 3, but it's negative 2. So that's negative 1 over 6u squared. If you simplify everything, we have one negative sign, we have a 3 times 2 is 6, and a u squared, but it needs to move to the bottom, plus c. And now I can put u back in place. I get negative 1 over 6 times u, which is 1 plus x cubed squared plus c. All right, so that's going to do it for this intro to U substitution.